Hello everyone, so this is the first video in our playlist and we're given a question with the concentric cylinders, and in the question we're given an already determined velocity profile in an angular direction and a gap between concentric cylinders where k is the ratio of inner to outer radii. So we're given a velocity profile, this equation. Let's just write it down here. So it is the velocity directed to the theta angle is equal to the omega, which is the angular frequency in radians per second, k squared over 1 minus k squared, which is k, where k is just the constant, which represents the ratio, and r squared, so r, big R is the outer radius, and where the small r is the independent variable in our question. And we're also given that k is equal to the ratio of inner to an outer radii. Okay, so which means our k should be equal to radius inner over the outer radius. Okay, so in a question we're asked to show that the torque in the inner and outer cylindrical surfaces are equal to each other. And we're also given a shear rate in cylindrical coordinates. So the last equation is the equation for the shear rate in cylindrical coordinate. Okay, so what we're going to do now, so here we're given the diagram of a concentric cylinders, and we're going to try to draw the diagram from the above. Okay, if we do this, so we're going to have something in this form, right? Where this part is a liquid. Okay, let's draw it this way. Okay, so where this part here is a liquid, right? So there's the inner radius and the outer radius, and what R in our question it represents is, so it's going to be any point. So the radius at any point, and right? So it's going to just represent the radius from any point from the center, and we're going to have a v theta directed to theta angle. Okay, so now we're going to start proving the torque in the inner and outer cylindrical surfaces are equal. So before that, let's discuss and take a look what's actually happening in our question. So if you remember, if you can imagine what's happening in this question, so it's very similar to a case where you stir something inside of a cup, and because of the liquid's motion of stirring, the cup also starts to move. So which proves that the torque is also torque inside of a cylinder, inside of a cup, and outside of the cup is equal. That's why the cup is also moving. So it's something very similar is happening with the cylinders. So in order to prove that they are equal to each other, we need to use the shear rate equation. So our shear rate equation is shear rate. Okay, so shear rate is equal to the radius multiplied by the derivative of the velocity directed at theta angle over radius, respect to radius. Okay. So here we have the equation for our v theta, right? So in order to express it as a shear stress, we have to divide it by r and take a derivative respect to r and multiply it by r. Okay, now we're gonna try to apply the same steps to our original equation. Okay, so if we divide the whole equation by r, we're gonna have v theta over r is equal to omega k squared over 1 minus k squared, and here we're gonna have r squared over so we're dividing by r, so it's going to be r squared minus 1, right? So that's what happens when we divide it by r. And now let's take a derivative from both sides respect to r. Okay, so then what we're gonna have is, so dr v theta over, so we're taking derivative respect to r from the both sides. So we're gonna have omega k squared, this is gonna be constant, and for the r we're gonna have, so we're taking in respect to r squared, right, the small r, so it's just gonna be negative 2 r squared over r cubed, right? Okay. And then what we have to do now is we're just gonna multiply it by r again, so that we're gonna express it in the form of a shear stress. A shear rate, sorry. Okay, so our shear rate is gonna be equal to r times dr v theta over r, and we're gonna multiply this whole thing by r, which makes it v k squared over 1 minus k squared minus 2 r squared over r, right? R squared. Okay, what we can do further is, here we have our relationship of k and the radius, right? So we can say that the shear rate, we can only consider the shear rate in the inner radius first, so that we can find the torque inside of an inner radius. So we know that our inner radius is going to be equal to k times the outer radius. So we can, when we find the shear rate at inner radius, this is going to be, so like omega k squared over 1 minus k squared minus 2 outer radius of outer cylinder squared. So this is going to be r I, so this is going to be the inner radius, so it's going to be k squared r squared. So now we can see that the k's are going to cancel, r's are going to cancel. So what we're left with is negative 2 omega, like angular frequency, over 1 minus k squared. So this is going to be the shear rate for our inner radius. Okay. So in the question we are asked to find the torque, right? So what is our torque? So the torque is going to be so like if we consider the torque inside of it, like of an inner radius, it's just going to be like force times inner radius. And we also know that we have something called shear stress, so that like shear stress is going to be equal to the viscosity times the shear rate, right? And our torque here is going to be equal to the shear stress times the area. So the area of our concentric cylinders is the circumference multiplied by the height. So it's going to be just 2 pi r 2 pi r, so we're considering the inner radius, so it's just going to be 2 pi r inner radius times h. So this is the area, right? But so this, the whole thing with including h, represents our force. So we have to multiply this by radius, inner radius, so that this is going to represent our torque. So if we substitute shear stress by viscosity times shear rate, here we already have a shear rate equation for our inner radius. So we can do some substitutions here. So our torque is going to be equal to viscosity times the shear rate at r is equal to ri, right? So it's going to be negative. So here what's happening with the negative is, we can kind of refer to it as the rotation to the clockwise or anti-clockwise. So kind of negative here does not really matter. So we can just write the 2 omega over 1 minus k squared, because we're not concerned about the direction yet. And then it is multiplied by h, and multiplied by inner radius. So this is, I think I forgot something. Yep, I forgot like 2 pi r. 2 pi radius, inner radius squared h. So yeah, so now this is how our torque at inner radius looks like. So now in order to find the torque in the outer radius, what we have to do is we first have to determine the shear rate at outer radius. So here we have already determined the shear rate, just the general equation for the shear rate here. So if we're going to replace r squared with outer radius are going to just cancel. So what we're going to have is, so like here, if we just replace this thing by big R, so these two r squares are going to get canceled. So what we're going to be left with is negative 2 omega, negative 2 omega k squared over 1 minus k squared from our equation. And again, we are not concerned about the direction, so we can just ignore the negative sign because it represents the direction of our motion. So, and then when we plug in it to the torque equation, it's just going to be again the viscosity times the shear rate at outer radius. So this equation, right? 1 minus k squared. And again, the multiple, so this is the force, right? And it's being, no, it's not the force, it's just the shear stress multiplied by the area, 2 pi r squared. So it's area times the inner, okay, so this is big R now. Area times the outer radius squared, because, yeah, area times, so this is the, okay, this is how we get it. So we're going to multiply circumference by height and by the outer radius. So I can just write it as r squared because we're multiplying it by r twice. And then what really happens with these two equations is we're just trying to prove if torque r is equal to inner radius is equal to torque r is equal to outer radius. So this is what our question is really asking for. So if we compare these two equations, so the viscosities are going to cancel, 2 is going to cancel, omega is going to cancel, gets canceled, and 2 pi is going to get canceled. And what we are left with is, so for this one, our inner radius squared over 1 minus k squared, 1 minus k squared, and for the outer radius, we have like outer radius k squared over 1 minus k squared. And so we have the same denominator, so they're going to get canceled. And if we compare the numerators, this, everything squared, so this reminds us about the first equation we had. So here we have the ratio of inner radius to the outer radius, right? So I'm just going to replace Ri by just this one. So we're going to have k squared, r squared is equal to k squared, r squared, which proves that our torques at inner radius surface is going to be equal to our torque at the outer radius surface. So this is how we got the answer for our first question, where we asked to show that the torque in the inner and outer cylindrical surfaces are equal using the already determined velocity profile and a shear rate equation at cylindrical coordinates. Thanks for your attention.